because we had a pole at s equals 0, our system is currently BIBO unstable, so we need some kind of controller in place. For this, we decided to do a proportional derivative controller, which gives us a kp constant and a kd constant. Our g of s comes right over here. And we also decided to say that our disturbance would be 0 because we're in a fairly isolated room, and we're already accounting for the air friction in our original model with the damper. So taking all this into account, this gives us a final transfer function. So while we haven't yet determined a Kp and Kd, we can still check the stability of this with the Routh-Horowitz test. Oops. This guy comes down. So in the Routh-Horowitz test, we need we basically need everything in the first column to be positive. So we get the following relationships in order to be stable. So these give us bounds that say that KD has to be more than -4 and KP has to be greater than 0. So those give us some nice bounds for KD. Next, we decided to do, for our design parameters, we decided on a settling time of less than 3 seconds. This had to be fairly small because it's a telesurgery robot, so you want to be fairly accurate and you don't want to have much delay between input and output. Percent overshoot less than or equal to 2% because you really don't want any of that error. And then, of course, steady state error we set to be 0. So if we plug these into our formulas for settling time, three seconds. Find that zeta omega n has to be less than or equal to 1.55. So we're going to have bounds right about there. And then our percent overshoot, plugging into the natural log formula, we get that zeta has to be more than or equal to 0.456. And the cos inverse of that gives us an angle of 62.8 degrees. So then we're also going to have bounds right about So this angle is going to be 62.8 degrees, and then we're going to have acceptable bounds are in this region. And this will make sure that we're stable.